Okay, hello, welcome everyone, good evening. So this will be the lecture Machine Learning for Physicists. My name is Florian Marquardt. I'm here at the Max Planck Institute for the Science of Light in Erlangen and also at the University. So regarding today, I will first give the lecture, the first lecture of this course, and then we will have some time also to discuss maybe some of the more organizational things. Please note that the lecture will be recorded. I mean, you are not in the picture. I am in the picture. Also, there's a website which I will direct you to afterwards. And there will be tutorials for this lecture offered as well for you, and they will be hands-on. So the whole principle of this lecture is to give you a hands-on experience with neural networks so that in the end you can really program even quite advanced stuff. Okay. So let us start. If you think of your brain, it is quite an amazing piece of software or hardware, as the case may be. And it is quite amazing in many respects, but especially also because it is very flexible. And if I am a physicist or mathematician and I want to boil down the workings of the brain to the most elementary model, I could say the brain is something which takes an input and generates an output. The output might be, for example, what I will talk to you or how I move around in the world. Now, how does that work inside your brain? And the amazing thing is that it works by electricity, by electrical signals. And this was realized already hundreds of years ago, but the microscopic details started to be understood about 100 years ago. And here's an actual drawing by Ramon y Cajal from Spain. He was one of the pioneers of investigating neurons in the brain. And so here you see that these are the bodies of these neuronal cells, and then there are many branches by which they can be connected to other neurons. And then there will be electrical signals traveling between all these neurons, and you can view these neurons as kinds of switches. And so if one gets activated, maybe another neuron also gets activated, and so on. So this lecture will not be about the biological workings of neurons, but of course this has inspired a lot of mathematicians and computer scientists, inspired them to try to invent something that is artificial, that works as an algorithm on a real computer as we know it, but that can be as flexible as the human mind. Because, in particular, what we want is something that works without you having to prescribe a detailed algorithm, but instead it should be able to learn on its own, just as your brain is able to learn on its own. So that's the purpose of inventing what is called artificial neural networks. So they are inspired by how a brain works. They do not exactly model how a brain works, but their goal is also to be as flexible and to be able to figure out new stuff by looking at training examples, essentially. And so here's a first picture of an artificial neural network. This is the kind of structure that we will be discussing throughout this lecture series. Very basically, it also consists of neurons. These neurons simply hold values, numerical values. There will be connections between these neurons. These connections can have different strengths. These strengths will change, and that will determine the functionality of such a neural network. Again, we will learn all the details in the course of this lecture series. But in the end, again, it takes an input, calculates a complicated nonlinear function of this input, and generates an output, and hopefully this output will be something useful. So what could be a typical example of a task that such a neural network can perform? So one of the most well-known and most powerful applications of neural networks are in image recognition. And the idea is that your input is really an image. So technically that would mean you decompose the image into many pixels, and then all of these pixels have values for the grayscale value or the color value of these pixels. You feed them into an artificial neural network. It does whatever it has to do, and it spits out maybe a number, but the number can be converted back into a word, and this word would then tell me oh, this picture represents a light bulb. Yeah? And so the task is, or the challenge is, to train such a neural network, to find a clever algorithm to train such a neural network to be able to recognize arbitrary images, even those that it has never seen before. It would be kind of simple, also a little bit silly, if it could only recognize images that are precisely exactly equal to something that it has been seen before, because for that it would just need a large memory and store all the images that it has ever seen. But it should be flexible enough to also recognize images of a light bulb that look a little bit different than what it has seen. And so that would mean, again, we will go through the details of these concepts, but the way it works practically, in practical terms, is you will have thousands and hundreds of thousands of so-called training images where you tell the network what would be the correct answer, for example, in this case, light bulb, and also many other images of objects that are not a light bulb. And after having seen all these training images and performed its clever training algorithm, it will then indeed be able to recognize arbitrary light bulbs as such. Okay, and so this concept, of course, has been around for quite some time. Later in this lecture, I will tell you a very brief rundown of the history of neural networks. But the real power of neural networks became apparent to all the world, I would say, back in 2012, because, you know, computer scientists like to make competitions. So they announce some challenge. In this case, it was a challenge to be able to recognize images. And then everyone can try to write clever algorithms and try to solve this challenge as good as possible. And so this particular computer scientist's challenge is called the Imagenet Competition. You are given 1 million training pictures showing different objects, each of which has been annotated by humans. So a human has selected whether this shows an eagle or a car and so on. And then you have to run your algorithm, whatever it is that you have invented, and later your algorithm is tested because it will be applied to images that it has never seen before and has to recognize these images and label these images and say, oh yes, this is definitely a horse, for example. And so in 2012, so this Imagenet competition had been around for some time, but in 2012, a neural network, in particular a neural network with many neurons and many neuron layers, so it was called a deep neural network. A neural network was able to beat all the competition, and since then this Imagenet competition has all the time been won by neural networks, and by now they are better than humans in recognizing pictures, especially, for example, if you try to recognize animals and then yes, you may recognize this is a horse, but which particular type of horse is it? And so these neural networks are very patient in training on many training examples, and so they can become really powerful. Okay, so this is when everyone was taking notice. And on this slide, I have listed a few example applications of neural networks. You can easily find more if you just Google on the internet. Recognizing images, I already told you. One can also do something more sophisticated. Instead of just saying a single word that is a label for the image, one can train a neural network to literally describe a given image in terms of a sentence. For example, it will say, oh, this picture shows a woman carrying an umbrella, for example. This might be a sentence that a neural network can generate by just looking at a picture. They can colorize images. What I mean by that is you have trained a neural network on many pairs of black and white or grayscale images and the corresponding color images, and then it learns to colorize arbitrary images, which means understanding a little bit about the meaning of images, understanding what's the typical color of, I don't know, the color of a lake, for example, should be blue. Neural networks have learned to translate languages, so you put in a string of sentences, you get out a string of sentences. So the current version of Google Translate, as far as I know, works on this level. They have been trained to answer questions about a brief text, so you tell the neural network a little story, and then you ask questions, and then it can answer these questions. So that's a little bit like what you would do with children in elementary school. And they have also been able to play games and play these games really at a superhuman level, so as to be able to beat the best humans in some of the games. And I will come back to that in a moment. Also in science and in physics, neural networks have been used and are now being used more and more. For example, you can look at many different materials and you want to predict, oh, for this kind of crystal, for this material, what's the melting point? That might be a typical question. And people have very large databases of many different materials. They have measured the melting points, and then you can train a neural network on this, and then you can ask it about material that you have never even fabricated maybe, and it tries to predict what should be the melting point. Okay. So now I want to show you, just to demonstrate the real power of these neural networks, I want to show you at least one example of something where we will learn later in this lecture series the technique that is actually behind it. And that is about these video games. So the particular video games that this company called DeepMind was investigating, a little bit old-fashioned from the 1980s. These are simple action games, so basically no big strategies are required. You just want to increase a high score by moving around some object. And the particular game where I will show you an example is called Breakout. So in Breakout, basically the idea is there are lots of stones. There's a little pedal that you can move around as a player from left to right. There will be a ball, as you will see in a moment, there will be a ball bouncing around. Whenever the ball hits a stone, it will eliminate the stone and your high score increases. And your task is, of course, to move the pedal in a smart way so that whenever the ball comes down here, it will actually hit the pedal and be reflected into the right direction. And your goal is simply to eliminate as many stones as possible in as short a time as possible. And so what these people did is they took these raw video images together with a high score to train a neural network. And they told the neural network nothing else but your task will be to increase the high score as much as possible. And the actions you can take are simply moving the pedal to the right or to the left. And the neural network started out with a completely random strategy in the beginning, but it learned, because whenever it wins or has a high score, it knows that the actions were presumably good actions. And so that's a technique called reinforcement learning. At the end of the lecture series, we will go into the details of this. But now I just want to show you in a video that they took how good this machine player, how good the neural network can become. So I'll just have to switch to the movie. Okay, so what you will see now at first is how the computer behaves after only a few training episodes when it has played a few games. And then successively you will be shown behavior when it has trained even more and more games, and eventually it becomes really good. In the beginning it's not very good. Often it will miss the ball. So here it goes. Well, it's not completely bad because it has trained a bit, but as you can see, sometimes it misses the ball. So now they have trained it for more training episodes. It still is not perfect, obviously. So now it has already become quite good. Most of the time it does hit the ball. But that's not yet the ultimate limit because it doesn't have any particular clever strategy. And that happens now after even more training because now it found a really good strategy. And when I first saw this, I was quite impressed, I have to say, because it builds a little tunnel to the left and then it shoots the ball behind the tunnel and it automatically will eliminate many, many stones. And so immediately the high score jumps to really large numbers. So that is what reinforcement learning and neural networks can do for you. And by now, this is of course a relatively simple action game. By now they are also trying such techniques on more complicated strategy games, for example. And the most famous example from just a few years ago is playing the game of Go, which is a board game which is supposed to be much more complicated than chess because you have many, many more possibilities than chess to make different moves. And yet they were able, after such training, to beat the human champions in the world. And that had never been achieved before with any other technique. Okay, so this is a little preview. So I now want to briefly tell you something about the lecture outline. And I also want to encourage you at this point to please always ask questions. Yeah? Sometimes I might be going a little bit too fast, maybe when it becomes a little bit more mathematical or when I try to show you some code. I know how to program in Python, but maybe you don't. So please stop me in these cases. So first we will learn something about the basic structure of these neural networks. And we will keep it simple and go step by step so you really know what you're doing. And then it's about training a network, not just having a network produce an output for a given input, that's nice, but trying to change the structure of the network so it becomes better and better and better, like in these training examples, and does the task that you invented for the network to do. For example, recognizing the images. And technically that has a word, it's called backpropagation. We will learn why it's called like this. Then we will go forward to more sophisticated neural networks that are really the neural networks that are used in these image recognition applications. And they are smart in that they exploit translational invariance. Translational invariance simply means that if there's a square in the upper right-hand corner of an image, it is a square. If the same kind of square sits in the lower left-hand corner of an image, it's still a square, so to speak. It doesn't really matter where it sits, and you can exploit this to make more efficient neural networks. Then I will tell you something about one particularly nice technique of unsupervised learning. So I told you so far that the usual application would be training, where you give a lot of input-output pairs, basically where you already give the correct answers. But there are techniques where even without having labeled anything, even without knowing any answers, you can still have, just by having a large data set, have a neural network learn something about the structure of this data set. And autoencoders are one particularly nice and simple example of that. And then we will move to more advanced things. One of them is about dealing with time series. So in physics, you have time series when you have a fluctuating voltage, for example, and in many other situations, you also have time series. Even when you have a sentence that is a series of words, that is also a kind of time series. And when you process such a time series as a neural network, it would be really good if you have some memory, because if you have forgotten what was the last word, then obviously you will not understand the sentence. Yeah? And so to cope with this, you want neural networks that have a memory, and these are called recurrent neural networks, and they are super useful in many applications. Then we will come to something that is equally interesting, especially from a physics point of view, and that is trying to imitate probability distributions. So here the goal is, I show you millions of images, for example, and you are able, that is the neural network is able to reproduce images that look kind of similar to all these millions of images that I've shown you, yeah? That are able to produce the typical images that you have seen. And so more technically, that would be about learning a probability distribution. In this case, it would be a probability distribution over images. So this image that shows a car, that is very probable because you have seen it many times, whereas this image that looks like completely random noise, that is not very probable because you have never seen such a weird image before. Okay. And then maybe as the most advanced technique that we will learn, we will really go to reinforcement learning, which is what I just told you about in learning to play these video games. So when you don't tell the computer what to do, you don't give the answers, you don't even know what is the best strategy to play Go, but you let the computer figure out the strategy on its own. And this is really the kind of technique that presumably if we ever go to real artificial intelligence, this is what we have to do, yeah? Because if we are always stuck with having to have a teacher that trains the neural network and tells it what to do, then of course how can we ever become better than the teacher? Okay. So, as I said before, the main purpose of these lectures is learning by doing or hands-on so that you can really program such neural networks. And I will split it into two parts basically. So in the very first lectures, I will use Python, this programming language. I handed out a few Python cheat sheets for you. I will use Python directly to program neural networks, just to show you, even without any sophisticated libraries or packages, you can make your own neural networks, you can make backpropagation, you can know exactly what's going on, yeah, without any secrets. But then there are so many more advanced techniques, maybe at some point it becomes a little bit cumbersome to try to program everything yourself. And so the good thing nowadays versus the situation, say, 5 years ago is that there are many really nice libraries or frameworks or packages that you can use, also several for Python, and you can use them to basically program to set up a neural network in 5 lines, for example, and you have a really sophisticated neural network, and then you can train it easily. So then the biggest amount of the code you write doesn't have anything to do with the technical details of neural networks anymore, but is, for example, only about generating the data or looking at the end result of the training or something like this. And so that's really, really useful. We will be using a high-level package that's called Keras, which is very popular with many people. And underlying this package is something called TensorFlow, which is one of these libraries that are around. TensorFlow is by Google, but there are also other such libraries. But the details, I will explain them when they matter, and also you don't even need to look into too many technical details. It's really, really simple to use. Okay. Any questions at this point about the outline? If not, as I said before, the organizational things maybe we can discuss at the end of the lecture today. So here's just one thing I want to point out. I gave this lecture already 2 years ago, and then I set up a website publicly. It's called Machine Learning for Physicists, and there you can see how the lecture sounded 2 years ago. And you can also see the slides of the lecture 2 years ago. And as we go along this time, I will revise and update, of course, the material and the slides. Okay, I will skip this, the calendar, because I will come back to that at the end. So now I want to start really by giving you a brief outline of the history of neural networks. And it's quite amazing that these are basically as old as computers, let's say. So it started more or less in the 1950s. So when people were taking the first baby steps in programming computers, they were already thinking about, can we make computers that are as smart as humans? Which would be something that you would call artificial intelligence. And so at the time, of course, when you know nothing, you are very bold and you think, maybe I can do this within 1 or 2 years. And so they were very bold, and they set up a workshop in 1956 in this case, and they really invented the first neural networks back at the time. These were very simple, they didn't have many neurons, only very few layers, and we will come back to them later. But this is basically how the whole thing started. Then I skip over a lot of details. There were various periods when people were disappointed again because they thought, oh, this should now work, and then they found out, no, in the version that we have implemented now, it doesn't really work, it cannot even do very simple things, and then they were too pessimistic, and it oscillated a little bit back and forth. And I invite you to, say, go to Wikipedia and read about the history of neural networks. But I skip all these ups and downs, and I'll just mention a few milestones that are a little bit arbitrarily selected. So one of the milestones was to invent an efficient algorithm for training these neural networks, and it's called backpropagation. As I said, I haven't yet explained why it's called like this. And that was, well, let's say first invented in the 1970s, but then came to the attention of everyone in the 1980s. Then in the 80s and 90s, also these more sophisticated neural network types were invented. For example, recurrent networks that have memory, convolutional networks that are really good for images. But you do have to understand that in these times, computers were not yet very powerful as compared to the laptop that you have today. So that means people were still struggling. And the problem is, so you have invented some algorithm. It should work. You think it could work, but you're not quite sure. And then you try it out on a few examples, and then it gets stuck, and it doesn't really work, or it only works for the simplest examples. And people were a little bit disappointed, and they were struggling to understand why it didn't work. Yeah? Nowadays, we know you have to have really large data sets. You have to have really a lot of computational power and really large neural networks, and then things start to work really well. But of course, at the time, they couldn't be sure, and so they were a little bit disappointed, and they invented various excuses why this gets stuck and why it might be a fundamental problem and so on. Okay. So then, however, there were a few intrepid scientists who went on, and in the early 2000s, they invented powerful techniques to train also neural networks that are large, that have many neurons, have many layers, and which we now know can become really, really powerful. So these are the so-called deep neural networks. And then there's the breakthrough, if you want, of the image recognition competition, and then everyone really took notice and understood that this is a really useful thing. Okay, so that's a very brief history, leaving out many things. So if you're interested to learn beyond the lectures in more detail about what I will tell you, there's two things I want to recommend. One is a very, very nice online book by Nielsen, who's actually a physicist. It's called Neural Networks and Deep Learning. And this covers basically the first few lectures that I will be giving. So it's really slow, and he really covers every detail. And then if you want to go beyond, maybe after the lectures, there's a big book called Deep Learning, and that really covers many, many of the sophisticated techniques. Maybe for any given technique, you only find a little information, but at least it covers all the important techniques. Okay. So now I really want to start. So now we really want to know, how does such a neural network really work? And what you can see here is, again, a picture of a neural network. But before we go into explaining what the blue circles mean and what the gray lines mean, I just want to reiterate that if you view it as a black box, a neural network is nothing but a function that takes an input and turns it into an output. For example, an image turns it into a word. And this function can be quite complicated. It can be a function that takes as input many variables, for example, the pixel values of an image. There might be 10,000, for example. And as its output, it could also have many values, for example, the many letters of a word, for example. And not only does it have possibly many input variables and many output variables, but more precisely, it's a function that is parametrized, because you want to change this function, because you want to train, and training means you have to be able to change this function. So internally, this function has many, many parameters. We are talking of 100,000 or so, maybe. And during training, these parameters will change. So it's a complicated nonlinear function with many variables that depends on many parameters. And many really means many. Okay. But the building blocks, the beauty is that the building blocks are very simple. The building blocks are these neurons and the connections between them. And so when we draw the structure of a neural network, we distinguish different layers. As you can see, there's a lowermost layer. We call this the input layer, where you feed in the input values. There are several layers that are neither the input layer nor the output layer. They are called the hidden layers. And then there's an output layer. Okay, so that's the overall structure, but people can also build more complicated structures, of course, still keeping the underlying basic structure of many neurons connected together, but maybe you don't have individual layers that you can distinguish. So one can get more complicated, but in what we will do, we always keep this layer structure. Okay, so now we zoom in. We look at a single neuron and how it works. So the purpose of such a neuron is to take the values of the neurons in a previous layer and calculate a new number, a new output. So the way to think of these blue circles, which are the neurons, is that each blue circle at any given time carries a number, a simple real number. And here for the neurons in the input layer, I labeled them Y1, Y2, Y3, and so on. So you just have an array of numbers. So the question is now, what does this neuron do with these numbers? Well, you have to understand that this neuron is connected to the input neurons by these gray lines, and each of these lines has a certain strength, or we will call it a weight, attached to it. Yeah? That also happens in your brain. Yeah? So sometimes there are connections between different neurons, sometimes the connections are weaker, and so on. And these will be the things that change during training. So I called these weights here W1, W2, W3. Later we will have a slightly more sophisticated notation because I have to distinguish all the different neurons. But for now, you see there's only a handful of different connections and each of them has its own weight. These weights are also simply numbers. And then what I want to do is, first I want to do something really simple. I want to take the weighted sum of the input values. So the weighted sum is written down here. It means multiplying each yj input value with the corresponding wj, which is the weight. So for example, w1 gets multiplied with y1, and w2 gets multiplied with y2, and so on, and then I sum them all up. So that means, for example, if one of the weights is 0, w2 might be 0, then the value of y2 will never contribute because it gets multiplied by 0. Okay, so that's a weighted sum. And then, to keep things really general, I want to add to this weighted sum some offset. That's nothing very deep. I'm just trying to write down the most general linear function of the input values. So just, you know this from school, if you have, if you want to describe a line in 2 dimensions, you would write it down like this, and here we just have more coordinates to deal with. Okay. So sometimes this is called offset, sometimes it's called bias, the W's are the weights. Now that will give me a result, and I will call this result Z. This is not yet the value that the neuron will carry. Rather, I will take this value Z and I will feed it into a nonlinear function that I call f. And I apply this nonlinear function f to the value z, and then that's the value that I will assign to my neuron. So that's why in this neuron I have depicted f of z. Yeah? So first take the linear operation, then apply a nonlinear operation. And the reason we want to do this is, if we didn't do this, if we were to forget about the nonlinear function f, then in each of the layers I only apply linear operations, and then you can really work it out very easily for yourself that also the connection between the lowest input layer and the highest output layer would simply be a linear function, and that's too simple to do anything amazing. Yeah? So all these neural networks have to have nonlinear function. But the good thing is this f, I do not need to make it dependent on any parameters. We are done with the parameters. The weights and the biases are enough. This f can be chosen fixed. It can be the same f for all the neurons in the neural network. It doesn't need to adapt during the training. I can choose some nonlinear function f. And so people like to choose very simple nonlinear functions. Here I show 2 examples. So what you want to do is you want to be inspired a little bit by biology. And in biology, it's observed, if you look at biological neural information processing, there's a kind of threshold behavior. So only if sufficiently many neurons are activated and are producing an electrical current, then also the higher neuron will start to fire and also produce an electrical current. And so this is modeled by these functions, because as a function of their input, z, the function, for example, is 0 all the time, and then it goes up to a finite value. Let's call it 1. Yeah? So it's like a step function. And for reasons that will become apparent later, we prefer not to have a sharp step function, but we prefer to have a smooth step function. That's good because you can take the gradient, you can take the derivative of a smooth function better than of a sharp function. Okay, so this function would be called sigmoid, but it doesn't really matter. A physicist might identify it as a Fermi-Dirac distribution. Anyway, you want to have a rounded step function. Another popular nonlinear function is displayed down here. It's called Relu, so people have these funny abbreviations. That's a rectified linear unit. You see that it is piecewise linear, so it is constant 0 for input values below 0. And it is just linear, maybe even with a 45-degree slope, just identity, for values of the input that are larger than 0. Yeah? But the interesting thing is still, even though it's piecewise linear, overall it's not a linear function, and that's enough. And people like this Relu function because then it's very quick to calculate the derivative, for example, yeah? Because the derivative is 0 to the left and plus 1 to the right. Okay. Maybe if you want to become famous, you can invent your own nonlinear function, but then you would have to prove that it really is somehow more efficient in training. But the good thing is it doesn't really matter. As long as you pick some nonlinear function, maybe preferably monotonic, your network will be able to train. Okay. So do you understand this working of a single neuron in principle? That's important, because if you don't understand that, you won't understand the networks. So it just takes a linear function and then applies a nonlinear function. The linear function has parameters that can change, that's important, but the nonlinear function is just kept fixed. Okay. And now the whole neural network just consists of many of these elementary building blocks. So you see, for example, here this neuron is connected to this neuron and that neuron, and maybe also to the others, but if the weights are 0, I don't even draw the line. And so this neuron will take a linear superposition of this value and that value and apply the nonlinear function, and that's it. And that will become the new value here. So overall, we can summarize the situation by saying each connection has a weight, W. Each neuron also has an offset B that appeared in this linear superposition. And each neuron has a nonlinear function, but it's usually the same for all the neurons, so it's fixed. And then the values of the input layer neurons are fed into the bottom, and one by one, layer by layer, you are calculating these output values until you arrive at the output layer, and then you are done. Then you have applied the neural network to the input, and the neural network has calculated an output for a given input. So I really want to, this is obviously important for the whole lecture, I really want to go through it step by step. Here I already provided a few values in the input layer. I just picked random values. And now I want to look at one of the neurons. All the rest will be the same. I want to calculate its value. So what I have to do is, I have to ask what are the weights. Sorry. Let's say they are 0.5 and 0.1. And so now I told you what we have to do. We have to multiply the 0.5 by the 0.1 value. And we have to multiply the 0.1 weight by the 1.3 value. And then we have to add it. And maybe add the offset, if we have one. So that's shown here. The z is this weighted sum. In this case, I neglected the offset, but I could add it. And then I will plug this value of z into my nonlinear function, and I get something. And for example, I might get 0.7. Yeah? And so I can now do this for all the other neurons in the same layer. And then I can do this for the higher layers, because now, of course, I can go to the neurons in the layer above because I know what I have to feed into those. And I go, and then finally I arrive at the output. And so this evaluation of the neural networks that I do layer by layer, it's called feed forward. It's feed forward because, well, you feed the input into the lowest layer, then you feed those values into the next layer and the next layer and so on. So it's feed forward from bottom to top. And this is, of course, also to distinguish it from what we will do in training, which is called backpropagation, which essentially does something similar but going from top to bottom. Okay, so this is clear, right? Okay, fine. So now if I want to implement this on a computer, I don't want to be stupid. Yeah? So I don't, for example, I do not want to give a different variable name to every different weight. Because if I have 100 weights in my neural network, it would really be very boring if I start calling variables W1, W2, W3, and so on, and then I write down the formulas, blah, blah, blah. So I need more efficient notation. Notation that, in the best case, is scalable. So if I want to add some extra layers, I don't have to invent new variable names and so on. And so here's where it's really useful that you are physicists. Yeah? Because maybe in another lecture I would have to tell you about matrix vector product and so on. But here, of course, you know this, and so I can refer back to that. And so our goal will be to write these things in terms of linear algebra, in terms of matrix vector product, and then everything will become really simple. So the first thing we have to do is we have to be a little bit precise about indices. So I want to give indices to all my neurons so that I can build the weighted sums. I also have to give indices to my weights and so on. I'm still very modest with my indices at the moment because later I will also have to introduce yet another index to distinguish the different layers of my network. Yeah? For now, we will not do this. We will only look at to connect one input layer to one output layer. And so then I can, for the moment, neglect these extra indices. But okay, so we have one output layer, we have one input layer. I will use for now the index j to number all my output neurons. So in this case, maybe j is 1 and j is 2, and these are all the two output neurons. And then there's an index k by which I number all my input neurons. And so now if I want to build this weighted sum, what I want to do is, for each input neuron, which I call yk in, and each output neuron, which I call j, I need a weight, because this yk at some point is connected to the output neuron j. Yeah? So all the different pairs of input and output neurons, they have a weight attached to them. So each weight actually has two indices, namely the index of the input neuron and the index of the output neuron. We didn't have that before because I only was talking about a single output neuron, but now I have several output neurons. Okay. So not surprisingly, if I want to write this down in the most general terms possible, I will take yk, the value yk of the input neuron, multiply it by a weight that as indices carries j and k, input and output. And then I want to build the weighted sum, which means summing up all the contributions of all the input neurons, just as before in the simpler example. And so here, all the input neurons would mean all the k. So I have to sum over k. Yeah? And then I will get a result that only depends on j, because I already summed over k. And that is the result that goes into output neuron number j. Okay? So I will call that zj. Remember, the z is not yet the value of the output neuron, it's just the thing that I will apply the nonlinear function f to. Okay. And then in addition, I will have some offset, b, and this offset will be different possibly for the two different output neurons. So for output neuron number 1, there will be some b1. For output neuron number 2, there will be some b2. Okay. So is this clear? I mean, I really wrote it down in detail with all the indices. And maybe at home you sit down again and write it down, but this is how I can write it down compactly. And now I can make it even more compact if I remember that these things that have various indices, I can interpret them as vectors and matrices. Yeah? So everything that has only one index obviously is a vector. Everything that has two indices is a matrix. Okay, so some people among you as physicists might protest that sometimes vectors should have a geometric meaning, and then in different bases they are represented by different numbers. So I'm not so sophisticated here. For me, a vector is just a set of numbers that sit in a column maybe, and a matrix is just a rectangular array of numbers. So that's what we understand here. So in matrix vector notation, I would say this sum over k, wj, k, yk, well, that looks like applying a matrix to a vector. It's the matrix W with its coefficients wj, k. And I have to sum over an index. I always have to sum over the inner index, so to speak. In this case, it's the index k. You see here, k sits to the right of the matrix, and also k comes in as the index of the vector. So this is really what you learn for the matrix vector multiplication. So I could write w times y in, and the result again would be a vector whose index is j. Okay? And then that's fine, because now bj, I can also say these are the components of a vector, and I just add this vector b. And then what I will get out is a vector z, again, whose components are the zj, so z1 and z2 in our case. Okay. So this is an even more compact notation. And that's very nice, because if we want to play around with it or implement it on the computer, then you can use matrix vector multiplication instead of writing down a for loop that does the sum. And this is not only nice because it's compact, but it's also much more efficient. Yeah? So we will be using an interpreted programming language, in this case Python. It is super inefficient to do inner loops in such an interpreted programming language where you run over many numbers. It's really, really bad. But whenever you can use something like a matrix vector multiplication, that is really efficient because it's built in. And it's also efficient for many other reasons, because then maybe one day you run it on a CPU, the other day you run it on a so-called graphical processing unit, GPU, and if you program it yourself, maybe you have to change the program, but if you use such more general linear algebra routines, it's super easy. Okay. And then finally, of course, we still have to apply our nonlinear function. Now this is something we want to do element-wise, because for each output neuron, we will apply the same nonlinear function, remember? So I would say that the value yj of the output neuron is just the nonlinear function f applied to the zj. Okay? So there, if you then implement this in a programming language, you have to make sure that you really apply a function element-wise. But again, there are very efficient ways of writing this down. Okay. So this is just basically what I've told you on this slide is, of course, nothing different from what I told you before. We have just made the notation more compact. Okay. So now there's a question here. Yes, please. Yes. Yes, so that was already the question? Yeah, okay, so I repeat the question so that everyone can hear. So the question was whether there's, in any kind of network, there's always just this feed forward. And I would say yes, in almost any kind of network. If you want to build in loops, then you have to think very hard about how the network is evaluated. This sometimes comes up when networks have memory, rather advanced networks that we will not even discuss, where you would then say, in one time step, I have all the values available in all the neurons of my network. And then when there's a loop, that's still okay, because I will propagate the values only during the next time step. You know, if you don't tell me how you go about such loops, it could be even ill-defined what is the result, yeah? But if you do it time step by time step, in principle, you can start to think about networks with loops, but we will never have networks with loops. Okay. Okay, good. So now we really want to implement this, and the programming language that we will be using, because it's very widespread and people like it and it's really nice to use, is Python. And I want to show you how this works, but maybe before we go there, okay, so now I have to see in which order I do things. So maybe, so here's something, you will be able to install Python and all the other packages in the tutorial that takes place next Monday. And we will be able to help you in installing these things. If you like, you can also already try to install it at home until then. But in any case, we will be there to help you. And what I'm showing you now is a kind of programming environment that people have invented for Python and many other programming languages. It's called Jupyter. It's a so-called notebook environment. That just means you keep track of whatever you enter and what is the output and what is the graphics that are produced. It's a little bit similar to what was introduced in Mathematica, if you know this. So you keep everything in a single notebook. And so this notebook now is running with Python. So whatever I enter will be Python code that is executed. Okay. So for example, I could just type 3 plus 4 and hit enter, and yes, 7 is the answer. I could also have variables and, for example, print what is the square of A. In Python notation, the square is with this double star notation. Okay, 25, that's correct. And I can have, for example, a loop. So you understand that I'm not giving you a full Python tutorial now. So what I tried is, first I handed out what I call a Python cheat sheet, so that you see a lot of simple examples, and once you install Python, you can just try them out. And also next time we will install Python and maybe do a little simple exercises with that. And here it's just to demonstrate for those of you who know maybe another programming language, how you would go about programming in Python. So for example, if I want to have a for loop, I could do things like for j in range 5. That tells me how long the for loop should run. In this case, it will run over the numbers 0, 1, 2, 3, 4. Yeah? So 5 numbers in total. And then I want to do something with the value of j that I get in this for loop. And so then there's a specialty about Python. In almost any other programming language, you would then write something like begin and end to say what are the instructions that are executed in every turn of the loop. Or you would have a curly bracket open, curly bracket close, or anything like that. In Python, it works a little bit differently. In Python, you just indent, so you have a set of spaces or a tab. You just indent the text so that it doesn't start at the beginning of the line. And that signals to Python that this is a block that now belongs to the for loop. So let's say we just want to print the square of these values. And yes, these are the squares. Okay, so this is a very convenient environment to do little experiments. And this is also the reason why people like to do an interpreter, and I like to teach this using an interpreted language instead of, say, C, because then you can easily try out things. Okay. So now let me get back briefly to explaining what we want to do with respect to our neural networks, because now we want to implement what I told you before in Python code. Yeah? And I just have to translate for you the matrix vector notation into Python notation. And so what I've written down here again is what we want to do using indices. Below I've written down what we want to do using matrix vector notation. And then I've written down how I can implement this using Python. More precisely, we will be using a package for linear algebra that's called NumPy, numerical Python, and that is able to do matrix vector multiplication. And the reason I display this here is not only to show the syntax, but in particular to teach you how the different dimensions of the vectors and matrices will get combined. So, if y is a vector that has a length n in, because n in is the number of input neurons, then w would be a matrix that is of dimensions n out times n in, yeah? Because it has to be multiplied onto this vector. So the dimensions I'm listing here always correspond to how many values these indices can take. So for example, the index k, which is the second index, it takes values 1, 2, 3, 4 if I have 4 input neurons. And so that would be the dimension n in. The output index j takes 2 values, 1 and 2 if I have 2 output neurons. And that would be the dimension n out. Yeah? And so you always, when you program, you have to keep track of these things because you can easily confuse yourself. And then this bias vector, that has an index j. J corresponds to the output neurons. In our case, there were 2. So that's the dimension n out. And so then, in order to do this matrix vector multiplication, which I wrote down here, in Python, you need to do nothing else but to say dot w, y. The dot reminds you of the dot product, which is the scalar product between two vectors, but here it's more generally also applied to, say, doing a matrix vector multiplication or maybe even a matrix-matrix multiplication. Okay. So this is the simple Python code. So instead of programming any for loop, you really just literally write this down. But I haven't yet shown you, for example, how to initialize these matrices and vectors, and so that's what I want to do now. Okay. Okay. So the first thing we have to do is to tell Python that we need this linear algebra package, which is called NumPy. So we have to import this package. And then, I don't know, maybe there are some people here among you who are already programming in Python. Can I have hands up? Whoever? Very many. That's good. That also means that you can help the others who don't yet program in Python. And those who do program in Python maybe sometimes are a little bit worried about my programming style because, well, I like to keep the notation short. And in order to keep it short, I will do things like from NumPy import star, which means that instead, if I want to apply a NumPy routine, instead of writing NumPy dot, I don't know, sine function or whatever I can apply in NumPy, I can directly apply the corresponding function. So I don't have to tell the computer that this is part of NumPy. So if you don't like this, if you want to use many different packages and want to distinguish the different functions, please don't do this. Okay, so now my computer crashed, or maybe only this crashed. This is not. Yes, please. There's another question. Mm-hmm. Yeah, let me just fix this first. I'm bad at multitasking, apparently. Okay, so this still works. That also works. Okay, good. Yeah, go ahead, ask your question. That's correct. At each layer, we apply a nonlinear function. Let me go back. Maybe here, for example. Yeah. So that is, here I'm only displaying the step from one layer to the next layer. So I apply F once. But I will go on later and of course take whatever I calculated for this output layer, I will take as an input for the next step. And then again I will apply F and so on. So this is only one step. So in the end, if you were to write down the value of an output neuron explicitly in terms of the values of the input neurons, it would be a very complicated repeated application of F. So there would be nested applications. So it would be F of blah, 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 of F of and so on. So it would really look very complicated. No one writes it down like this, but this is what would happen. Okay, so now the computer has stopped thinking and I can show you a little bit. So, okay, I import this NumPy package. But then I want to initialize, for example, the weight matrix. I want to initialize this bias vector. And for that purpose, I first have to tell it, okay, what is the size of my input layer? What's the size of my output layer? I don't want to keep them fixed in the code because maybe later I want to change them. So I introduce these variables. I call N0 will hold the size of the input layer, in this case 3. N1 will be the size of the output layer, in this case 2. And then I want to generate, for example, an array or a matrix W that holds all the weights. Remember, this should be a matrix of dimensions output layer times input layer. In this case, N1 times N0. And I have decided to fill it with random entries because I didn't know better and we don't do training at the moment. So you can use in Python this random function, and random.uniform will just give you uniformly distributed random numbers, and you can even pick between which borders these numbers will be. So in this case, I say low equals -1, high equals +1. I just get randomly uniformly distributed numbers between -1 and +1. And with the size, I really literally tell it my matrix has to be of this size, N1 times N0. So the first index of this matrix going forward, the first index will always have a length N1. The second index will have a length or a number of different values N0. So that's fine. And then I do the same for the bias vector. Remember, that's just a vector. And as its size, it has the number of output neurons, which here was called N1. So I do the same instead of a matrix. However, it's just a vector. So I hope that this doesn't mean that it gets stuck, that it is stuck again. Okay, so now it works. Okay, fine. Now I want to give it some input values. Again, I could do random input values, but here I just chose 3 particular input values. And at that point, I can also tell you the syntax for those of you who don't know how to create such a vector. In this case, you call it an array. So in brackets, you give the numbers separated by commas, and then you'd say it array, and this is the kind of array that you can apply matrix vector multiplication to, for example. So that I call yn. And then here in this line, this is where really all the action happens, because now I first do the linear superposition. So I take this matrix vector multiplication. W is applied to yn. That's the first term here. And then I add the bias vector b. And the result I call z. Yeah? And then I take this z and I want to feed it into my nonlinear function f. Now here I could have defined now a function that I call f, but here I write it down explicitly. And in this case, I take the sigmoid function. You can, if you like, you can plot this function as a function of z, and you will find that it really is a rounded step function. And you see the beauty of the kind of array syntax that Python offers. Remember, z is still, in our case, a two-dimensional, an array with 2 entries, an array with 2 numbers. But I can just pretend as if it were a single number. and I apply a function like the exponential function to it, and what will happen is that the exponential function is applied to each element individually. And the output will be, again, a vector that has each element the correct element. And so y out will now be a two-dimensional vector. So let's do this. And now I can print the results. And you see, okay, this was the input vector, 0.2, 0.4, minus 0.1. This was the matrix W. It's interesting to look at the structure. So you see the first line has 3 entries. This corresponds to the fact that the second index of W, that corresponds to the input neurons, can run through 3 values. And then there's only one second line, again with 3 values. The fact that there are only 2 lines for W means that the output index, which is the first index of W, only can take 2 values because we only have 2 output neurons. So I will later tell you where on the website you can find this kind of program, and then you can play around with it and change things and see what changes. Okay. B, you see, this is again a vector, but only with 2 numbers because that corresponds to the 2 output neurons. Z also has 2 numbers, that's the 2 output neurons, and Y out, similarly, that's also the 2 output neurons. So you see at least our very simple-minded neural network that only has 1 input layer and 1 output layer and nothing in between. We were able to do this, and we already wrote it in a fashion that is extensible. So now I could, for example, instead of having an input layer size 3, I could write 100, and output layer could be 200, and it would still work. I would only have to give more input values, and the rest of the code doesn't need to change. Yeah? So that's already nice. So are there questions about this? So this is the most important step, the one that I'm highlighting now. Okay, so I suggest that maybe you want to try to install Python at home if you don't have it yet. And even if you don't succeed, come to next Monday's tutorial where my assistants will be around to help you install everything, including these more advanced frameworks. Right now we are not using any advanced framework. We're just using plain vanilla Python. So if on your computer, for example on Linux, maybe you have Python pre-installed, this is it. Okay, so let's see. Okay, let me return for a moment to the actual lecture. This is what I explained to you. We produce some random weights and biases, we have some input values, and we apply the network, and we can print the result. It's very good to think of these networks also a little bit in graphical terms. For example, if I have only 2 input neurons, then I can represent their values in a 2-dimensional plane. So any combination of these 2 values defines a point in the 2-dimensional plane. And then if I only have 1 output neuron, that's just 1 scalar value. So now I can literally draw the function that the network implements. I can draw it for you because it's a function with 2 input arguments and 1 output argument. So I can make a 3-dimensional drawing. The vertical axis would be the output of a neural network, and the 2 axes, y1 and y2, are the 2 inputs of the neural network, and I can literally draw what happens. And so now I can first draw the step where we only do the linear operation. And the linear operation, I remind you, would be to take the weighted sum of the input values and add a single offset value, b in this case. It's just a number. And what's the result? We call it the result z. And if I want to plot the result, well, since it's linear, the result must look like a plane. Yeah? So I take 2 input values, I calculate a linear function, I plot this linear function, the result will look like a plane. So this is the blue plane that I'm plotting here. Now I said we always also want to apply a nonlinear function. And these nonlinear functions are often chosen such that they somehow distinguish between negative argument and positive argument. For example, this rounded sigmoid step function, if the argument is negative, it gives 0 mostly. If the argument is positive, it gives 1, apart from the little rounding. Yeah? So in order to figure out what the application of f does when I apply it to z, I have to track where z is positive and negative. But that's also easy in this geometrical way of plotting things, because if z is depicting this blue plane, then all the values of z that are positive, they obviously lie above the coordinate plane y1, y2. They lie above the red plane. And all the negative values lie below the plane. Yeah? So that means if I now apply such a rounded step function f, which takes all negative values to 0 and all positive values to 1, this is what happens. So now the blue thing is no longer z, but f of z. It has turned all the positive values into 1, more or less, and all the negative values into 0. And so that's how it looks like. You clearly see it looks like a rounded step function. Yeah? But now not in 1 dimension, but in 2 dimensions. And so 3D would be one way to represent it. You can also represent it in the way that I show up here, which is basically a color plot. So red values go towards 1, blue values go towards 0, anything in between is some color in between. And so the horizontal axis would be y1, the vertical axis would be y2, and what I'm plotting in terms of color scale would be f of z. Yeah? Okay, so I want to show this also to you in an actual program. So, well, let us first get slightly more sophisticated. I like to define this action of calculating the output neurons from the input neurons. I want to define this as a function, because later I want to apply it repeatedly to go layer by layer from the input to the output. Yeah? And so here I define a little function. I call it apply net. It takes as input this value, this vector of input values of the input neurons. There are some global variables. Again, the purists will not like it, but I prefer it to keep the notation simple. So the W and the B already exist as variables that hold the weights and the biases. Then I apply my calculation of Z, just like before. And then I return the result that I get if I also apply the nonlinear function. So what will happen is I put in some input value vector, and I get out the output value vector. So this function really does one step from one layer to the next. Okay. So now I go ahead again, and I want to initialize all my weights, all my biases. In this case now I take a slightly smaller input layer with only 2 values. That's because I want to visualize things. So just like I showed you just on the slide, I want to have only 2 coordinates. And the output layer is very simple. It only has 1 value because I want to visualize it in terms of 1 value that I want to plot. Okay, but the rest is the same. And now, instead of doing all the steps individually, I really apply my function, which I called apply net. So I feed in the input vector, and hopefully I get out an output vector, which in this case only has a single value because I only have 1 output neuron. But if there were more, then I would get a larger vector. Okay. So that's good. That just meant we have made things a little bit more efficient, but nothing really changed. And now I want to plot the results. Yeah? So for all different possible input values, y1, y2, so for all different coordinates in the plane, I want to plot the output. Yeah? How do you plot in Python? Well, there's a wonderful library called matplotlib, which I import here. And so now I have to decide if I want to plot things. Probably I cannot plot everything in the whole infinite 2-dimensional plane, obviously. So I have to take a small version of it, and I also have to choose a certain resolution. So maybe I do a 50 by 50 pixel image, and I run through the different values of y1 and y2 and calculate the corresponding output value. So it's probably not worthwhile going into the details here. I'm doing it here in a very stupid way. So if you're programming Python, don't do it like this. I really implement inner loops. So I run through all possible 50 values on the horizontal axis and all possible 50 values on the vertical axis, and then calculate the corresponding output. So the details are not so important here. We will do it more efficiently later. But what is important is that for each of these values in the two-dimensional plane that I loop through, for each of these pairs of values, value 0 and value 1, they correspond to y1 and y2, I apply my network here. And then the network outputs a vector, but from this vector, which only has a single entry, I only want to take this single entry as a number, so I take this single entry. And one thing to notice about Python or NumPy is that the entries of a vector are numbered 0, 1, 2, 3, 4, 5. So if you want to have the first entry, it's the entry number 0, as in any reasonable programming language. So, and then I want to store the output in a big array, because in the end I want to plot this array, because in the end I want to show you how this looks like. Okay. So this I did now do. I mean, nowadays computers are so fast, even if I run through 2,500 value combinations, you don't even notice. And then I can plot the image, and this is the image. It looks different any time I run the program, because I initialize my weights and biases randomly, so the output will also look random slightly. But what you see, the horizontal axis would correspond to y1, the vertical axis to y2, and the color values again, black means 0, yellow means 1, and then you get anything in between. So the smoothed step function. Okay. So here I wanted to be slow enough that in principle you could follow, at least in these initial steps. I now want to be slightly faster just to demonstrate to you what would happen if I don't only apply this procedure once, but I apply it many times. Remember, this was only one step from the input layer to one output layer. But now I can go on and I apply the same function again and again and again. So I have multiple layers, one after the other. Yeah? And so in this way, I will be able to produce much more complicated functions, because each additional layer produces another layer of complexity, so to speak. And so we want to just try this out empirically now without going very much into the details here. Just use the function that I currently use to have a single step, use it repeatedly to build a more complicated function. Yeah? And so here I define a function that applies a single layer, which is basically similar to what I did before, with the only exception that now I also feed the weights and the biases to this function, because now there will not only be one set of weights and biases, but for each new step from layer to layer there will be a different set of weights and biases. So I need to generalize my function a little bit, so it also takes the weights and biases. And now you see I start to define multiple layers. I still have an input layer, I call its length n0. I have an output layer, call its length n2. But I already have a first so-called hidden layer, I call its length n1. And so then now I need weights that connect the input to the hidden layer, and I need other weights that connect the hidden layer to the output layer. Yeah? So these here I call W1, going from input to hidden, and W2 going from hidden to output. And now you see the structure. Yeah? I could go on and on defining more and more weights. And for each of these weight matrices, I really have to be careful about their size. The size is always the size of the output layer times the size of the input layer. Yeah? So here, for example, the input layer of the first step is the literal input layer of the whole network, n0, but the output layer of the first step is the hidden layer, so N1. And in the next step, I go from N1 to N2. So if you've trained this a little bit, you realize the structure and it's not very complicated anymore. Only the first time you see it, you think there are a little bit too many indices. Okay. So these are my weights and biases. I initialize them randomly. Now I define a function that applies the network as a whole, which just means in succession applying the first step and the second step. So from the input to the hidden and the hidden to the output layer. So here you see twice I apply the apply layer function, and that's enough. The first one has weights W1 from input to hidden. The second has weights W2 from hidden to output. So again, these are probably things when you see them the first time, it looks a little bit confusing, but if you go through it slowly, it's actually not very complicated. Okay, so again, I want to draw, so I chose here deliberately only 2 input neurons and only 1 output neuron. The hidden layer has more neurons, but the input is 2-dimensional, the output is 1-dimensional. The reason is purely because I want to visualize it. Yeah? So I do this now, I fill in my image, and the result you see is already quite a bit more complicated than what we had before. What we had before, I can show it again. It's a very simple thing. Basically, in this 2-dimensional plane, there is a line, this greenish line, that separates high values from low values, and that's all. And when I run the same program again and again for different random values, it will always look like this. Very simple. But now, you see, things get quite a bit more complicated. So this is obviously no longer a simple line. Yeah? And now I promise that things get even more complicated, which is good for us, if we move to more layers. Why is it good for us? Because in the end, we want to be able to train arbitrary complicated functions from input to output. And we can do this only if, by adding many layers, the neural network has the power to represent complicated functions. And so, well, I will now skip a little bit. Let me skip a few technical steps here. Yeah. Okay, so this is where I wanted to go. So we will now just do the same, but with many hidden layers. And then again, the input is still 2-dimensional, the output is 1-dimensional. We will raster through the image of possible input values in this 2-dimensional plane. We will plot the output value as a color. But now I have many layers, and I promise it will become a very complicated looking function. And so this is the function that it generates. It almost looks random. It's not really random. This is only a function of me not having enough resolution. So if I run it with more resolution, it takes a bit longer. But as you can see, the image it generates is really, really complex. So again, this is a neural network. It takes 2 input values, which are here plotted as the horizontal and vertical coordinate. And the output value is plotted as the color. And it can obviously represent a really, really complicated image. Now, this image is not very useful, but we will later learn how to train it to reproduce completely arbitrary images. Yeah? Okay. And so I would say at this point, I really want to stop the lecture for today. So that would also be the end of the video. And we will still take a few minutes to talk about organizational questions. Okay. But maybe before we go to organizational questions, are there still any questions you have about the material so far? Yeah, please. Okay, very good question. So the question was, sometimes for real brains, they can reconstruct a missing piece of an image, right? And so actually people have trained artificial neural networks to do the same. So they have shown many images that had some parts blocked out, and then shown the corresponding images that are complete. And then the network really learns to be able to reconstruct the parts of the image that are missing. Okay, good question. Is there a threshold? I suppose there is, but I don't know the numbers. But it would be interesting to figure this out. Another question? You mean when I say my images? It's not completely random in that there's obviously correlations between the color values. So it's not as random as completely white noise. But it's random in the sense it was created by having random arbitrary weight values and is not good for anything. So I haven't trained it to produce a particular target image. This is what I mean. So if you were to, so now it gets a little bit complicated. This, of course, is only one single image generated for one particular network with a particular choice of random values. I could go, for example, to do statistics. I could, for example, make a little game where I produce many such neural networks with different random weights. Then I could look at these pictures, and then I could use the tools of statistical physics, let's say correlation functions, to calculate the spatial correlation between these pixels. There would be a certain correlation length even, and that has then to do with the structure of the neural network and the size of the typical spread of the weights. I wouldn't even know what would be the result here. It would be a good homework, I guess. So it's random, but random in an interesting way, I would say. Mm-hmm. Okay. Any more questions? No? Okay, so then we really stop the lecture as such. But I wanted to go back to discuss the logistics. Okay, so there will be tutorials, or maybe I first go to the calendar. So the only constraint for me is that I'm traveling quite a bit, so that means I'm not here every week. But that's no problem. You will get the total amount of lectures that is promised, which just means that in some weeks I will give lectures twice a week, 2 times 2 hours. And in some weeks I'm simply not here and will not give lectures. But what we offer is in those weeks we will have tutorials. So the tutorials amount to on average 1 hour per week throughout the semester. But what we really do is that sometimes, indicated by these red spots, we have a 2-hour tutorial, and then there's a break, and then there's again a 2-hour tutorial, and so on. And these tutorials will be given by my assistants, Ricardo, Victor, and Leopoldo. And the tutorials are supposed to be quite hands-on. So you bring your laptops. Next time you can install stuff. And then we will work out interesting examples where you can really start to make your neural networks. So the first question I have, so I chose, well, first of all, I chose this time slot because I know from experience that it makes it easier for many of you to come if it's more in the evening, because then it doesn't collide with anything. And I chose Monday and Wednesday for no particular big reason. It's just something that doesn't immediately collide with anything that I know of. But do you have remarks about this? If there are no remarks about this, then still we can decide. So we can decide, for example, to start at 6 o'clock sharp, which means we then stop at 7:30, if that is better for people. Okay, good. So then from now on, we start at 6 o'clock sharp. This is true for both the lecture and also the tutorials then. Yeah? Okay, so I will upload this calendar to the So in principle, this calendar is also in the UniVis, but I still upload the graphical calendar onto StudOn. So there is a StudOn group, which I just created today. It would be really good if you could all somehow register with this StudOn group if you are students and can access this. Because then I can, if I want to send emails, I can then very easily send an email around to all the members of this StudOn group, and so it reaches you. I know there are also some that are not students, for example, from the Max Planck Institute, so I will have to have an additional mailing list, I guess. Yeah, please. Okay, so I was too stupid to set all the settings correctly, I guess. Does it say anything why you cannot join? Okay, good. Maybe we can check this online. Okay. Oops. Okay, maybe I should do this offline. Okay, so I will fix it. But then it's really good because I can send around an email to everyone. Okay, so let me go back. Yeah, so this is all for this. There's then still a question about exams. So I offer an exam if you want to take the credit points. But maybe we will wait a little bit with selecting the date until the exams for the more regular courses have been scheduled, right? I often find this is better than if I set it now. And I mean, the typical choices would be in the last week of the semester, the first week outside the semester, maybe even the second week outside the semester, but something on this order. Yeah. Okay, good. And, well, you can always reach me by email. If I don't reply, maybe send a second email. Okay, so see you then. Okay, so there will be a tutorial next Monday, but I will not be there at the tutorial, but okay. And then the next lecture is actually on May 6th. Okay, see you. Yeah. Yep. I cannot make it mandatory, but I really want to offer it to you. This is where you really get the hands-on experience. With the exam, of course, it's always a little bit difficult to make an exam for a lecture that is a lot of hands-on programming. I still have to think about how I will do it. Yeah? But it's highly recommended to go to the tutorial in any case because you really learn stuff there. Okay, see you next time.